So let's look at this one together. So the first thing you want to do is rewrite that y prime as a dy dx, just so you can visually see where things need to go. There we go. And then we're going to subtract that over. This piece, I'm going to subtract this whole thing over. So I have dy dx equals negative y x plus 1. All right. I'm going to move the y to the other side. So I'm going to have 1 over y here, dx. And I'm going to have negative x minus 1. Oh, no, dy, sorry. Let's do this. dy and negative x minus 1 dx. I just distributed that negative there. All right. Now I'm going to do my integration. Integration of y is just ln, right? Integration here, add 1 and divide, right? And so you're going to end up with negative 1/2 x squared minus, this becomes x, right? And then we have plus c. Get rid of your natural log here. And so you're going to get rid of that with your e. So we have e and the e to this whole big thing here. On the left-hand side, obviously it cancels out. So you have just your y, right? On the right-hand side, remember if you have your addition, it's just like e to that power times it. So you can say e to the c here times e to the negative x squared over 2 minus x. And this is just a constant here. So you can really just replace e to the c with c, because that's just a constant. E to the c is just a constant. And so you can rewrite this whole thing right here, y equals c, e to the negative x squared over 2 minus x. And now that we have that, we can go to our initial condition, which they gave us right here. Plug in all your x's with a negative 2, all your y's with a 1, and then solve for c. So we would say 1 equals c e to the negative 2 squared over 2 minus negative 2. You end up with e to the 0 here. So you say 1 equals c e to the 0, so c equals 1. Because negative 2 squared is 4, and then a negative 4 over 2 is negative 2 minus a negative 2 is 0. And then you can just rewrite this right here, plugging in your c. So we have y equals 1 e to the negative x squared over 2 minus x. And if you wanted to do a common denominator there and make it like negative x squared minus 2x over 2, you could. It's, you know, those are the same. Something like that if you want to. They're the same thing. It's just a common denominator. So the instructions here said find all function, or find an equation of the graph that passes through the point and has the indicated slope. So once again, we are going to want to rewrite your y prime as dy dx here. So I'm going to say dy dx equals 2y over 3x. And then I'm going to move the y over with division. And so I'm going to say 1 over y dy. And I'm actually going to say 2/3. There's a reason I'm doing this. 1 over x dx. It's easier to see that 1 over x, how the antiderivative is taken there. And so we're going to do integration here. And if you have a coefficient, right, it can go in front of your integration like that. So we have natural log of y equals 2/3 natural log of x plus c. There's a couple ways you can do this. You can actually put that 2/3 up in the x. I think it's easier to do it that way because then it gets a little less confusing. So you're gonna condense that natural log on the right hand side before we do the e piece of it. So natural log of x to the 2/3, right, plus c. And then we can do our base e to get rid of those natural logs. So on the left-hand side, we have y. On the right-hand side, remember, when we have addition in there, that's just two bases with the same. So we have e to the c times e to the natural log of x to the 2/3. And so what happens on over here is this is just a constant, and those two cancel out. So we have y equals c x to the 2/3. And now we can do our initial condition here. And so our x is 8 and our y is 2. And so we would do 2 equals c at, not x, 8. 8 to the 2/3. Remember, 2/3 is just the cubed root of 8 squared, right? So the cubed root of 8 is 2. 2 squared is 4. So we have 2 equals c times 4. So c is going to equal 1/2 here. And so we just plug that back into this right here. So we have y equals 1/2 x to the 2/3. So arcsine. So we know arcsine, arccosine, arctangent, arccotangent, arcsecant, arccosecant. That is just your inverse sine, your inverse cosine. On your calculator, it has to the -1. This is what happens when you are finding the angle given the trig function. All right, that's all those are. Arcsine, arccosine, etc. This is when you are doing the inverse of the trig function. So it would be like division compared to multiplication, right? In this case, they give you the domain and range. The domain of sine, well, sine can only go from -1 to +1. If you put into your calculator, what's the arcsine of 5, it's going to give you an error. You're outside of your domain, right? Go to your domain is typically what it will tell you, unless you have a... So, domain, meaning your x value, what you input into your arcsine, cannot be outside of that. Range, if we recall when we did this with unit circle, for the sine, they only take the first and the fourth quadrant. Because if you used the entire unit circle, you would have repeated values. Like if I said, what's the arcsine of 1/2? Well, it's 30 degrees or pi over 6, right? That's what would give me a sine of 1/2. If I did not limit it to the first and fourth quadrant, which is what this range is doing, then I would have to also tell you that not only is pi over 6 give you a 1/2, so does 5 pi over 6. And so I would have to tell you both of those that give you those signs. And so all this chart is doing is saying, okay, y is the arcsine of x if and only if the sine of y equals x. All right, I could say pi over 6 is the arcsine of 1/2, and if and only if the sine of pi over 6 equals 1/2. That is true, right? And then the domain and range just limit the values of it. You'll notice that tangent and cotangent are infinite. So think about right angle trigonometry. Sine and cosine from SOHCAHTOA. Sine is what? SOHCAHTOA, what is sine? So if you take the opposite over the hypotenuse, your hypotenuse is always your longest side. There is no way you will be over 1 because you have put your longest side in the denominator, sine and cosine. That's why your range can only go from -1 to +1. However, tangent is your opposite over adjacent and your cotangent is adjacent over opposite, right? And so for those, it can really be anything because you have two sides that can be any length. Your secant and your cosecant have to both be bigger than, the absolute value has to be greater than 1. That's the same thing as saying between -1 and +1. All right. So this is just trig functions you've used before and their domains and ranges. Now we're going to start talking about evaluating them, which we've done before, and then doing the antiderivatives and derivatives of them.
Nice.
All right, let's look at these. Arcsine of -1/2. All right, so arcsine of -1/2. The arcsine can only be in the first quadrant and in the fourth quadrant. And so we are looking for the reference angle of pi/6 in the fourth quadrant, which is going to be just basically -pi/6, your negative angle in the fourth quadrant here. On your unit circle, it will look like 11 pi/6, right? But you'll remember, if you recall from last year, when you are talking about arcsine, they want you to consider from 0 to pi/2. So from 0 to pi/2, and then from 0 to -pi/2, right? And so anytime you see a negative sine or tangent, you can really just use the negative angle of it. So a pi/6 would give you 1/2, a negative pi/6 would give you -1/2, all right? That's not true for cosine, but it is true for this. So negative pi/6. Arc cosine of 0. So for cosine, remember, we consider first and second quadrant. You go from 0 to pi for cosine. All right, and this is because that includes both positive and negative angles. So arc cosine of 0, what angle gives you a cosine of 0? Pi/2. All right. Tangents are a little more difficult, right? Arctangent of square root of 3. Arctangent of square root of 3. This is the angle that will give you a sine of square root of 3/2 and a cosine of 1/2. So this one's going to be, no, not pi/6. That's 30 degrees. pi/60 angle. pi/3. So square root of 3/2 as a sine as your y value. Now for this last one, this is not on the unit circle. So you need to take your calculators, right? Calculators. This guy's not on the unit circle. So in your calculator, you're going to use your sine to the -1, which is your shift or your second button. I don't know which one it is on your calculators. Opens parentheses there, 0.3, and then round to 4 decimal places. 0.3047, by the way. If -1 if x is between -1 and 1, y is between -pi/2 and pi/2, the sine of the arcsine of x is x, and the arcsine of sine y is y. These were the strange ones we did in pre-cal. So basically you're working from the inside out. As long as the inside meets the criteria of the function, it's just going to counterbalance itself. It's like saying, if I take 3 and multiply by 2 and then divide by 2, I'm going to get 3, right? If you take a function, its inverse, and you put them together, you're going to end up with where you started, is all it's saying. As long as it falls within the parameters of what you can do here. And so what they're saying is you can use a function to counterbalance its inverse, just like we've been using natural log with e. All right, so look at the example they gave us here. Solve this equation. The arctangent of 2x minus 3 equals pi/4. Okay, well then just take the tangent of both sides. So if I have this one right here, I can say, well, the tangent of this side and the tangent of that side, right? And so what happens here is my tangents and my arctangent cancel each other out. So I have 2x minus 3 equals the tangent of pi/4. And pi/4 is my square root of 2/2s. So my tangent of pi/4 is just 1 So I end up with something like this. Easy enough. It's just saying that tangents and that functions and their inverses can cancel each other out, which is nothing new. We've done that before. All right, derivatives of inverse trigonometric functions. So we have done derivatives of trig functions. We've actually done all 6 derivatives of all 6 of them now, okay? And so these are now the derivatives of the inverse. They look very daunting. Again, you need to memorize them, honestly. It's because what's going to happen is you will need to recognize them to go backwards to do antiderivatives. So arc sine of u being a function, is the derivative of that function over the square root of 1 minus that function squared. Cosine is the same thing, except it's just a negative. Tangent is the derivative of u over 1 plus u squared, and the arc cotangent is the same thing, just the negative on top. And then the secant and the cosecant also go together. U prime over absolute value of u squared minus 1 in the root, and then this cosecant is the same thing, just a negative. So they do pair up, sine and cosine, tangent and cotangent, secant and cosecant. But you do need to memorize these because it's not going to come naturally to know them. Let's look at how they're used. All right. So if you look at these examples, the arc sine of 2x, they want the derivative of it. So you go to the arc sine derivative. We are going to look, the u piece of this is the 2x. So the numerator here is going to be the derivative of 2x, that's just 2, right? Over the square root of 1 minus, and then my function, my 2x squared. And so that's going to be 2 over the square root of 1 minus 4x squared. So it's just a matter of memorizing them and being able to do them. Look at the next one, 3x for tangent. You go to arc tangent. I'm going to do the derivative of the u, my u being the 3x on top, that's my 3, over 1 plus my function, which is 3x squared. So it's going to be 3 over 1 plus 9x squared. All right, see how this is working. For this one, it's a little bit more difficult. My function here is square root of x, and we're doing sine again. So the derivative of square root of x is 1/2 x to the negative 1/2, right? We're going to put that over square root of 1 minus the square root of x squared. What happens here is my 2 and my x to the 1/2 go to the bottom. So I end up with 1 on top, 2 and square root of x on bottom, as well as the square root of 1 minus x on bottom as well. And remember, when you multiply roots, you can just multiply what's inside. So you end up with 1 over 2 square root of x minus x squared. And then for the last one, my function here is e to the 2x, and we're doing arc secant. And so remember, derivative of e to the 2x is just e to the 2x times the derivative of 2x, so that's times 2. Over, I'm going to do, it has absolute value of u, but e is always positive because it's 2.17 blah, blah, blah to a number. And so you don't even have to worry about the absolute value there for the e because it's always positive. No matter what you take e to, it's going to be positive. So you can leave the absolute value off here. So just e to the 2x and the square root of e to the 2x squared minus 1. You can do some simplification here. So here, my e to the 2x's will cancel, right? And then we can simplify that 2x squared. You just multiply these. Remember, a power to a power, you just multiply. So it's e to the 4x minus 1. So they want us to differentiate this particular problem. And to be completely honest, I feel like the easiest part of this differentiation is the arc sign. Because on the right hand of that plus sign, you're going to have a product rule with a chain rule. And so, I mean, the arc sign is really the least of your concerns right now. But it will turn into something that you can see that you're going to end up with like a common denominator. So anyway, so what I'm going to do here is I'm going to do the derivative of this piece, and then I'm going to use the product rule here to do the derivative of this piece. All right? The arc sign's easy. I do the derivative of x, which is just 1, over the square root of 1 minus x squared. That's the derivative of arc cosine. For the next one, I'm going to do product rule. Derivative of the first, derivative of x is 1, times the second. The second one is the square root of 1 minus x squared, plus the first, derivative of the second. So here we go. Derivative of the second is going to be 1/2 1 minus x squared to the negative 1/2, right? Times derivative of the inside, which is negative 2x. And so I want to rewrite this piece of it over here. Obviously, it's not pretty the way it is. And so I'm going to put this in the denominator so that I can see a little bit about what's going on. So here, my 2 is going to end up in the denominator because it's a 1/2. My negative 2x and my x will end up in the numerator. So I have a negative 2x squared over, and I have this 2 right there. And then I'm going to rewrite this as the square root of 1 minus x squared, because it'll let me see what's going on a little bit better. You can see my 2's will cancel. You can also see that I'm very quickly developing a common denominator. So my common denominator is going to be this 1 minus x squared. So I'm actually going to go ahead and multiply the top and bottom here by 1 minus x squared. What happens when I multiply this numerator by 1 minus x squared? Yeah, it cancels the root, right? I just multiplied top and bottom by square root. And so what happens is if I multiply this by itself, which is what I'm really doing, I end up with just 1 minus x squared there. So I have 1 over the square root of 1 minus x squared plus 1 minus x squared over the square root of 1 minus x squared minus x squared over the square root of 1 minus x squared. Okay. So we end up with 2 minus 2x squared over the square root of 1 minus x squared. So they simplified more. I don't know that you would know to do this, but maybe. So they multiplied the top and bottom by the square root of 1 minus x squared, and then they pulled a 2 out and had 1 minus x squared and canceled it out. So I'll show you how they got what they did. I don't think anyone would ever think to keep going here, but whatever, I'll show you what they did. So they did this. They rationalized the denominator is what they did. So we rationalize it, getting the root out of the denominator, right? And so what happens here is on the top, you end up with 2 minus 2x squared times square root of 1 minus x squared. And on the bottom, you end up with 1 minus x squared. And then they factored out a 2 and had 1 minus x squared here. And they canceled those guys. So they end up with 2 square root of 1 minus x squared. If you thought to rationalize the denominator there, that's what you would do. Most people would not think to do that. Typically, you rationalize a denominator when you have like square root of 2 in it. You don't, I mean, it's not required that you would rationalize a denominator. The reason I show you this is if you had a standardized test and one of your answers did not look like this guy right here, but it looked like this guy right here, you may want to recognize that you're just not done with the simplification based on a standardized test type question. Photographer is taking a picture of a 4-foot painting hung in an art gallery. The camera lens is 1 foot below the lower edge of the painting as shown in the figure. How far should the camera be from the painting to maximize the angle subtended by the camera lens? So they've given us a picture. Beta here is theta minus alpha here. So we have, this is the whole angle. This is the two pieces of that angle. So they want to compare this. How far away does this need to be? To maximize the angle. Maximize the angle. We know this side to be 5 feet, right? So we know this is going to be the 1 plus that. So if we're looking at, here's what we have set up. We have this angle equals this angle minus, like I'm going to be able to draw that little fish there. That angle. Really, I mean, B equals X minus A. We'll just do that. All Greek letters. Let's make them all Greek letters. Just for fun. When my pen does not want to work. All right, so here's what we've said. We've said this angle here is just the angle from the direct from the lens itself minus the little angle that's created underneath the picture. All right. And so they want to maximize beta. They want to maximize that angle. Maximize means I'm taking the derivative, right? And so anytime you see max or min, you need to think derivative. And so that's where they're getting this guy right here. Now, how'd they get cotangent? Well, tangent's opposite over adjacent, right? Opposite over adjacent. And so the cotangent of theta is going to be the 5 over the x, right? So I have cotangent, arc cotangent rather, because I don't have the angle. The arc cotangent of this guy here. And then we're going to subtract the arc cotangent of the little alpha piece, which is just going to be x over 1, adjacent over opposite, x over 1. So we would say arc cotangent of just x. And then we're gonna do the functions here. So if we were to do cotangent, go back to your cotangent. It looks just like tangent, but it's negative, right? So we do the negative derivative of that guy over the 1 plus the function squared. So the negative derivative of x over 5 is just negative 1/5 over 1 plus x over 5 squared. And we're going to do the same thing here. Minus the negative derivative of x is just negative 1 over 1 plus x squared. All right. And then all the rest of it's just simplification. Like they just literally did algebra here. When you do the square of this, you're going to have x squared over 25. So we have negative 1/5, 1 plus x squared over 25. When you get a common denominator here, you get 25 over 25. So we're going to say plus 1 because it's minus a negative 1 plus x squared. Here they got a common denominator, 25 over 25. And then they did keep, change, flip, by the way. So we have, just to show you your keep, change, flip. I'm going to move this out of the way, running out of room. We have negative 1/5 over 25 plus x squared over 25, right? So we did if you do over to the side, negative 1/5 times 25 over 25 plus x squared, you're going to get where these cancel out. So that's where we're getting our negative 5 from. All right. So we end up, this whole thing simplifies to negative 5 over 25 plus x squared plus 1 over 1 plus x squared. And then they just did a common denominator. So they just really your common denominator are these two guys, and they just multiplied. What I will say is maximize is where you have a critical value, so where it equals 0. Both of the denominators can never be 0, so you're never going to have an undefined. So it's just the numerator, which is where they ended up with the square root of 5, because it ends up with 5 minus, x squared. And so square root of 5 is what they ended up with as your maximum point. That's your only critical point, is square root of 5. And so they actually just put that in and plugged it into their original equation to figure out what it would be. They just used a really difficult one to show this maximizing. What I want you to move past the difficulty of is maximizing should lend you to first derivative equal to 0, no matter what your derivative looks like. No matter what your derivative looks like. So just because we had a crazy derivative because it had arc cotangents, your goal with maximizing is first derivative equal to 0. And that's all they've done here.